In this video, I'll show you how a unipolar PWM works and how you can use it to control a full-bridge PWM. So basically, a full-bridge PWM controls the output voltage by controlling the switches here. So we generate the gate signals by using a unipolar PWM here. And now this is basically how the output voltage would look like at the end. So the output voltage would switch between 0 and 400 when the reference voltage, the desired output voltage, is above 0. And when it's below 0, it switches between minus 400 and 0. Now, in order to explain how a unipolar PWM works, we first have to go through a little bit on how we calculate the output voltage. So the output voltage, let's just call it Vout, VO for now. It is equal to this voltage minus this voltage. So it's equal to VM1 minus VM2. Now quickly, VM1 is equal to the input voltage multiplied with the gate signal 1. Because if the gate signal 1 is 1, then we have current conducting through here, it is closed. So the voltage here would be equal to the voltage here. So then we get a voltage equal to a VM, then VM1 becomes equal to Vin, which is expressed by this equation here. And now if S1 is 0, then this voltage would be equal to this voltage because all of the voltage would flow through here instead. So then we multiply with 0, so then it becomes 0. And we can do the same thing for the other voltage, VM2. So this is equal to Vin and then multiplied by S2 this time. So if we just insert these voltages for Vout, we will get Vout as Vin, I will just factorize it, multiplied by S1 minus S2. Now I will just clear this up a little bit now. So we got Vout is equal to Vin, the input voltage, multiplied by S1 minus S2. Now, in order to control the gate signals, we should actually have the average model for the output voltage instead, because that is more desirable. So we will replace these with duty cycles instead, so D1 and D2. And the duty cycle is basically the average of the gate signal. So if we write it up again, so we have the output voltage is equal to the input voltage multiplied with D1 minus D2. And now the idea of the unipolar PWM is that duty cycle 2, the duty cycle of this switch, this should be equal to 1 minus the duty cycle of this switch. And now, if we just insert that for the output voltage, we will this time get the input voltage multiplied with 2 D1 and then minus 1. So this is the equation for the output voltage. And we can solve for the duty cycle to get the desired duty cycle. So we get, I will just do this quickly. So we have Vout over 2 Vin, and then plus 1/2. And then D2 would be just 1 minus this. And then we can use a PWM to get the gate signals, S1 and S2. So this is what we have written in this document here. So you can see that we get the duty cycle 1 is, so you can see that duty cycle 1 is 1/2 plus the output voltage. So Vref is the output voltage. It's the desired output voltage. And then over 2 input voltage, over 2 times the input voltage. And then the duty cycle 2 would be 1/2 minus this term. And then in the block diagram, it will look something like this. So we have, first we generate the gate signal, this is D1, and then we take 1 minus D1 to get D2, and then we have PWMs to get S1 and S2. So here we have a numerical example for this. So if we define the input voltage to be 400 volts, and then the reference voltage, which is the desired output voltage, to be a sinusoidal signal with an amplitude of 400 volts. And then we also need to define the switching frequency and carrier for the PWMs. So we have a switching frequency of 1 kilohertz, and this is just a fancy way to write a triangular waveform. And then we calculate the PWM. So first we calculate the duty cycle D1 with the equation that we just derived, and then we use a PWM to get the gate signal. And then we do something similar for the duty cycle 2. And then we use the equation for the inverter itself to get the output voltage. So this is just what the hardware does in the actual inverter. And then we have a unipolar, and then we have a moving average to just take the average of the output voltage. So if we just plot this, you can see that we have the reference voltage, which is the dashed green line here. And then the actual output voltage that we generate is the blue one. So you can see that it switches first it switches between 0 and 400. And then the average becomes almost equal to the reference voltage. And you can see that here it switches between 0 and minus 400. And here are the duty cycles that we calculated with the Python script. So you can see that D1 or D2 is equal to 1 minus D1, as you see here. And then we have the carrier here. So if we compare for example, duty cycle 1 to the carrier, when D1 is above the carrier, we get a gate signal of 1. And when it's not, we get a gate signal of 0. And we can do the same thing for this other S2. Now in my next video, I will go through how you can make this in Simulink and simulate it yourself. And if you want this document here, which is a mini course on 3 different PWM strategies for a full-bridge inverter, where I explain the full-bridge inverter and also how a PWM works. And I explain bipolar PWM and the standard PWM, and the standard unipolar PWM, which is the PWM that we went through now, and a variant of a unipolar PWM as well. And I will also have Python examples for all of these. So if you want that, you can go to the link in the description. And I'm also making YouTube videos for all of these topics here. So if you see this video, then I have a video on bipolar PWM and also have a video on how a full bridge inverter works and also how a PWM works.